Swayam Prabha. Digital India. Educated India.
Hello everyone, and welcome back this is a new series of lessons. In this one and the next few lessons we are going to learn the essential aspects of subsurface investigation. Now today's lesson we are going to talk about some introductory aspects of the subject, and we are going to learn a few things about how record keepings are to be done. Before we carry on with the presentation of today's topic, we are going to discuss the questions that were asked as part of the last presentation. The first question was, what are the main differences in sediment transport by flowing water and wind? So essential difference, the basic processes involved in sediment transport by both water and wind are quite similar, but the basic difference arises because of the fact that the buoyant weight of the sediment particles that are being transported by these agents, they vary quite a bit, because the unit weight under ambient conditions of air is about 1/1000th of that of water. So what happens because of that is in case of wind, secondary suspension, secondary transport, a transportation process is triggered because of some secondary effects. For example, saltating clasts, if they go and hit another particle when they land near at the ground surface, then those particles, because of collision, may actually get transported because of their being taken into suspension and transported. So this kind of sediment transport process, this type of secondary triggering of sediment transport process is not generally observed in case of water transport. The second question that was asked was, why ice laid deposits are usually poorly sorted while fluvial and aeolian deposits are usually well sorted. Now ice can actually transport huge sized clasts, say up to boulder size clasts, and as a result the spectrum of grain sizes that are present in an ice laid sediment actually covers a very wide range of grain sizes, whereas that kind of capability is not there when you are considering agents like water and wind. As a result, the grain size distribution is actually it varies over a very narrow band. So because of this fundamental reason, the ice laid deposits are going to be a little bit more rich in representing grain sizes as compared to sediments laid by water transport and wind. Then the third question that was asked was, name two poorly sorted deposits laid in marine and fluvial environments. In marine environments, the sediments that are laid, they are generally relatively very fine grained, because very low velocity environment, because of the very low velocity environments that generally prevails near the bottom of the ocean. In some cases though, the velocity can actually go up quite substantially, and that may trigger processes which you are aware on the ground, counterparts of which are known to you, known to many of you. If it takes place on the ground, such as landslide, subaerial landslide, those kind of processes also take place underwater, and they actually provide a very high velocity or high energy transportation environment. And in those environments, if a large grain size distribution is available within the sediment that is undergoing submarine landslide, then the deposits that are going to form when the landslide debris flow to a different location also have got representation from a very large spectrum of grain sizes. So in some situations, turbidites could have a little bit more wide grain size distributions than the mud deposits, so called mud deposits, that are found at the bottom of an ocean known as pelagic mud. Now the fluvial, as far as fluvial environment is concerned, one type of deposit that comes to mind is the deposits laid in alluvial fans. So in that situation, a high energy mountain stream actually enters a very flat lying area, and suddenly the velocity of the water flow decreases quite substantially. As a result, all the sediments that are being carried, all the grain sizes that are being carried by the mountain stream, they get deposited within the alluvial fan. As a result, alluvial fans have got a very heterogeneous structure, which often includes lenses of very fine grained material within coarser matrices or vice versa. The fourth question actually involves explanation of a few terms. The first one was point bar. So in this case, the deposits actually it is basically a fluvial deposit, and let us consider a meandering stream, and the meandering stream is going like this, and say this is the flow direction. So what happens actually on the insides of the curve, the velocities are usually smaller in comparison with the velocity near the outside. So this is the inside of a curve, and this particular for this particular bend, this is the outside of the curve. So here you have got higher velocity, and that often triggers actually erosion, and what you have got in the inside is relatively smaller velocity, and this triggers deposition, and since this particular deposit deposition is taking place right near the margin of the or perimeter of this particular stream, so the velocity is relatively much higher compared to a velocity which is laterally farther away from the stream bank. So what you get here, the deposits that form in this process, they are rich in coarser grains, and this type of deposit is called point bar deposits. Okay, so that actually explains the term point bar. Reverting back, The second question was what is meant by Kame moraine, Kame glacial deposit, and this is a sort of long ridge like deposit that forms because of meltwater, glacial meltwater, streams of which actually flow underneath the ice surface, underneath the surface of the ice, and they deposit coarser grained sediments such as sand, actually varying within silt and gravel size particles. These ridges are called Kame deposits. Now, the third type of the third part of the fourth question is involves explanation of the word Yardang. So, this is also a long drawn out ridge, but in this case the erosional process that is responsible for development of this type of landform is basically wind erosion, and because of that softer unidirectional, if the wind direction is relatively uniform in a single direction, then they actually eat up relatively softer areas of the bedrock surface, and what is left with, what you are left with is a long ridge of jutting out from a relatively flatter surface. So, this type of deposit, this type of landform actually is called Yardang. Okay, so that takes care of the questions. So, what we do now is to move to the subject matter of today's presentation. First of all, the objectives, what we want to learn from this particular presentation. We are going to learn the processes, essential processes of subsurface investigation of the stratigraphic condition underground and groundwater condition. We are going to list the plans or considerations that are involved in developing a subsurface investigation program, and we also are going to learn how to maintain an appropriate field record of the investigation activities in order to help the designer to pass on the information to the designer or to the engineer about what was the likely condition of subsurface deposits in terms of joints or open formed structures or groundwater and so on and so forth, because these are very important clues that the engineer will require in designing a particular facility at that site. So, these are the three main objectives of this particular lesson. Now, we consider the objectives actually of the subsurface investigation activities themselves. So, why we after all undertake subsurface investigation. So, what we want to find after we develop or conduct a subsurface investigation program. So, first of all, what we need to find, what we are interested to find is to identify and delineate geologic units. For example, a particular site may be underlain by a layer of soil. So, this one here is a layer of say sand, and then underneath that layer there could be a layer of silty clay. We do not know actually in engineering terms what are the meanings, what are the actual meanings of these terms but we are going to learn those things later on in the text when we talk about the textural classification of soils, as we did in case of rock earlier. Now, underneath the silty clay there could be a sandstone bedrock, which could be interlayered with interlayered say siltstone, and underneath the sandstone layer there could be a siltstone layer. So, in a subsurface from a subsurface investigation, what we want to find, we want to actually find the sequence of these subsurface units that are going to be underlaying that are going to be below underneath a particular site. We also want to find how the layers, these individual layers, thicken or thins out in a particular direction. So, we not only want to find these thicknesses of individual units, we also want to find the slope of these units. These, if you recall, this slope is called the dip of these interbeds or these interfaces. So, this is what we want to actually find in a sense from a subsurface investigation, one of the things that we want to find from a subsurface investigation. Then the second thing is, we want to describe each of those units systematically, and this description should include information on field identification of these units. For instance, the inspector needs to say whether the layer that is being encountered during the subsurface investigation is that consisting of sand size particles, or it is mainly composed of clay size particles, or whether it is sandstone or limestone or what have you. So, this is required to be identified in the field itself, and we will see how these things are recorded later on in this particular presentation. And the second thing is also is important is the extent of weathering or density or compressibility of these units. We need to identify the features such as joints, faults and slicken sides. Some of these terms are known to you, some of these terms are not. We are going to explain these terms later on, the unknown terms later on. This is important is because these joints, faults and slicken sides, they actually present planes of weaknesses which might be acting in future after the construction of a facility on top of this particular formation as planes of weaknesses, through which failure, ground failure might be triggered because of the change in the stress regime caused by the construction. Then the fourth particular thing that we are interested to find from subsurface investigation is we conduct simple index tests during the investigation itself to get a picture about how strong is the subsurface unit against a certain type of load. We continue with the list of objectives. Subsurface investigation also quite often involves assessment of hydrogeologic condition. What we want to find in this case, how the groundwater underneath a particular area is what is the condition of groundwater that is there within the subsurface deposit underneath a site. Then we want to extract also samples of geologic units such as different types of soils or different types of rocks for subsequent laboratory testing. We also sometimes sample groundwater samples, extract groundwater samples for laboratory chemical tests. And finally, another important objective of subsurface investigation is to install instrumentation which is going to be left in the left underground for monitoring of the time dependent changes of subsurface conditions, such as whether say for example, if the groundwater flow it has got a seasonal variation, then how the groundwater regime varies over time, we want to know that, whether it rises to the surface or what depth it actually falls to. This has got implication in the design of a particular facility at that site. So these are the main objectives of a subsurface investigation program. All right. Now, first question that comes to mind is how much of an area is to be covered in a subsurface investigation program. Now, the spatial coverage actually depends on the purpose of investigation and subsurface variability. Now, if an investigation is being undertaken for a very important project, then the spatial coverage may actually have to extend a little bit further out of the footprint of that particular project or the proposed construction, so that the effect of the proposed construction on the surrounding areas is also properly assessed during the design process. Then the second thing is how much of variability is there in the subsurface condition. If the ground condition is highly variable, that means the layers are highly irregular and they do not show any particular continuity over a large lateral extent. In that situation, the investigation locations need to be relatively close spaced in comparison with a situation where the ground condition is relatively homogeneous and uniform. Then the second aspect that actually governs the spatial coverage of a subsurface investigation program is how much of an area is being proposed for the construction of a facility. So the spatial coverage should at least cover the project area, and then, as I indicated just a few minutes back, the extent of coverage of the subsurface investigation should also cover an area outside of the perimeter if required, because this allows the designer to assess the influence of a particular construction on the surrounding facilities which is not within the project area. So let us try to understand what is meant. We have dealt with this thing some time back, this aspect some time back. Let us say there is a hillside, and this hillside what is proposed is construction of a hill road on the side of the hill, and what we are looking here is a vertical section, really vertical section of a hill slope. So, this is the proposed highway. So, this one is the proposed highway. Now, you could actually argue that since the highway is proceeding in a plane perpendicular to the tablet here, what we are going to do, we are going to drill a series of investigation hole along the center of the right of way, and that's going to be that is going to be it. Now, whether that is sufficient or not, that is what we want to actually find out here. Now, let us say this particular hill slope is underlain by a jointed rock, and the joint set, one of the joint sets is oriented in this manner. Now, if you have got this kind of joint set, so this is the joint set. If you have got this type of joint set, then if your proposed investigation of drilling through bedrock is only along the highway center line, then you are not going to be, you won't be able to see what is the dip of the joint as you move laterally from the center line of the proposed highway. So, in order to capture the geometry of the joint sets, we have to have subsidiary investigation downslope and upslope of the center line of the proposed highway. So, we need to have a set of boreholes laid out in this manner, and then we can easily find out the elevations from the drilling information from these boreholes of a particular bedding or a particular joint, and then we have got a better idea, better picture of the dip of the joint set in a direction perpendicular to the proposed highway. Now, that is important, that is very important, is because if we are proposing a highway through a hillside which is underlain by a jointed rock with a joint set like this, then if you excavate in this manner as shown, that is going to be triggering a possibility of rock slides, as we have learned from a presentation some time back. So, this type of orientation, joint orientation, is not really very good for the highway facility proposed here. So, instead of that, what we also learned earlier is that a preferable orientation of joint set would be like this. So, if the joints were to be oriented like this, then if you have got a steep cut at this location, then the cut is going to be relatively more stable. So, these considerations are verified from having a well laid out investigation, subsurface investigation plan. Okay. So, you saw there that we not only need to investigate along the proposed alignment of the highway, we also investigated laterally a little bit further out from the center line of the highway. So, that is what is meant in the last particular point here. So, you should take a note of this particular aspect as well. Okay. Now, the second question that comes to mind is what should be the spacing and depth of the locations of the investigation program. To what depth actually we should carry out the subsurface investigation, and what should be the spacing in between two consecutive locations of investigation. Now, it is quite obvious if the investigation is for deciding the preliminary alignment of a particular linear facility such as highway or a railway, then the investigation can be carried out at a relatively wider spacing in comparison with the corresponding investigation that is being undertaken for a detailed design project of the same facility. So, what a guideline in this respect is given on this table here. If you have got a preliminary investigation and if you have got uniform subsurface conditions, if the subsurface condition is relatively uniform, then a spacing of 100 to 150 millimeter between two consecutive investigation locations is often considered sufficient. Now, if you have got a very important structure and the project, it is the project is at a detailed design stage and condition of the subsurface layers is uniform once again, in that case the spacing is going to be much less, and the common practice is to go for boreholes every one borehole every 30 meters, or there should be one exploration location covering approximately 1000 square meter area. Then the third guidance that you have got in this respect is that if the subsurface condition is highly variable, that means the layers, the subsurface layers, they are steeply dipping and they are also pinching out or thickening in all different directions. In that kind of situation, subsurface spacing should be even less, and 10 to 15 meter spacing between two consecutive boreholes is often considered sufficient in this respect. Then we also have to find up to what depth we have to investigate, and a simple guidance in this respect, it concerns the change in vertical stress. So, the guidance goes like this: if the change in vertical stress is 10% or less of the initial vertical stress, then that should be the level up to which we want to conduct an investigation. So, let us try to understand this particular point a little bit more. Let us say we have got a ground surface like this. So, this one is the ground surface, and again we are looking at a vertical section, and let us say we want to actually construct an embankment dam at this location. Embankment dam at this location. Now, because of this dam construction, the soil elements underneath the dam, it will feel a larger vertical pressure in comparison with its original value. So, let us say originally you had a vertical pressure at that level of sigma v prime that arose because of a soil column of that much of depth. So, this was the original vertical pressure. So, if you consider the unit weight of the soil column to be gamma and the depth from the surface, ground surface, before the embankment dam was constructed, that was gamma d. Then after the dam is constructed, roughly you will also have to include the weight because of the material used in dam construction as well. So, this has got a unit weight of gamma 1 and this depth is say d1. So, what you have got here is finally is a pressure of gamma 1 d1. So, initially, so what you had here, so let us call it sigma Vf, where sigma Vf is the overburden pressure after construction, and sigma Vi is the initial overburden pressure So, in this case sigma Vi is equal to, as we have said in the sketch there, is equal to actually is equal to gamma times d, whereas sigma Vf is equal to gamma times d plus gamma 1 d1. Now, what happens actually as you go down deeper, the effect of the construction, effect of the weight of the embankment, it actually decays with depth. So, what we have got actually, if you consider the final overburden pressure, then as you go down deeper, let us erase a little bit more in order to get clarity. So, what you have got, sigma Vf decreases, or delta sigma Vf, if we plot sigma Vi minus sigma Vf. So, this one here is sorry, sigma Vf minus sigma Vi. So, this value is actually sigma Vf minus sigma Vi at a given depth, So, this actually decreases gradually with depth typically. Now, typically the overburden pressure sigma Vi, so this is both these things are being plotted against depth. Sigma Vi actually is going to gradually increase with depth, and let us say we are plotting sigma Vi divided by 10. So, 10% of sigma Vi we are plotting, and you can see that this is the depth up to which sigma Vf minus sigma Vi is greater than or equal to 0.1 times sigma Vi. So, basically this much of depth requires investigation, subsurface investigation. Okay, so that up to that depth you have to conduct the subsurface investigation. Okay. Now, we look at the different types of methods, that we normally used, that are normally used in subsurface investigation. So, one class of methods that involves actually inserting a probe or getting or intruding into the subsurface layers. So, this type of investigation is called the intrusive method. So, intrusive method includes all those methods of drilling, sampling and in situ testing. This also includes excavation of a test pit. We are going to look at the procedures later on, and it also includes trenching. And secondly, there could be non-intrusive methods. These methods do not involve insertion of a particular probe in the ground, and we will see the salient features of these methods later on in one of the future presentations, and they include seismic velocity profiling, ground penetrating radar and electromagnetic and resistivity surveys. So, here we do not actually intrude in the subsurface deposits, whereas in intrusive methods, some of which are going to be discussed today, we are going to actually insert something, a probe or a drill stem or something into the subsurface deposit. Now, before we get into the processes, we want to actually see the details. Actually, we are going to let me get the point straight. We are going to talk about intrusive methods in the next presentation, and non-intrusive methods we are going to look at the details of these methods in one of the later presentations after the next. Now, we want to actually look at the record keepings before we get into the procedural details of the intrusive method and non-intrusive methods, because it is extremely important. Actually, I should underscore this thing, it should not be treated lightly. It is extremely important to have a very complete record about whatever is going on during the subsurface investigation, because the investigator's report is the only thing that actually gives the details of the different types of happenings during the subsurface investigation to the designer of a particular facility, and if the records are incomplete, then the inference that the designer is going to draw from the field record is going to be insufficient and often misleading. So, what are the different aspects that must be included in a subsurface investigation field report? First of all, you need to very clearly mention the inspector should very clearly mention what is the exact location and time of investigation. And for this particular purpose, it is often essential, particularly when an investigation is undertaken for a detailed project design stage, it is very essential to have the locations of investigation properly surveyed in terms of their top elevation or the elevation of the ground surface at the location of the investigation, as well as the exact location of the investigation referenced to some benchmarks or the surveying monuments, or in terms of GPS coordinates. The second thing that must be included on the field log is the name of the person who is logging, as well as the name of the driller, because if the designer needs some information regarding activities regarding activities which are not appropriately mentioned on the field log, which are missed out from the field log, in that case the personnel who signs off the field log, they can be conducted. Then third thing is description of the equipment and procedure used in a particular investigation. That actually tells a lot about how much of a reliability can be placed on the information presented in the field log. That depends very strongly on the procedure used in the investigation. Then the fourth aspect that must be included in the field log itself is the log of material characteristics, or what kind of layers are being encountered during the investigation process. Then there should be a log of ongoing activity, and that should include whether any significant all significant occurrences, such as, for example, let us consider a drilling activity that is being undertaken at a site underlain by jointed bedrock, and there could be actually a cavity inside a bedrock because of removal of rock material by water or some other because of some other reasons. And if a drill stem is allowed to be lowered within that cavity, then what is going to happen if there is an effort to drill through this particular cavity, then the drill rods and the drill bit is going to drop through the cavity, and the inspector must record that the drill string dropped through a certain depth when the borehole proceeded to a particular elevation, because that will tell the designer that there are cavities within bedrock which must have to be considered while designing a particular facility on top of that surface. Now, if that information is missing, then the designer will assume that the bedrock has got no opening, and the strength that he is going to infer is going to be relatively more, and stability issue will not be considered in the design because of the presence of those cavities. So these type of details regarding the ongoing activity must be included in the field log itself. Then there should be groundwater observation, whether the water flow, water used in the progress of the drill hole that actually is lost within a cavity, that also should be mentioned here, water loss. Then installation details of any instrumentation like standpipe piezometer. We are going to look at the details of these particular we are going to look at the details of these things later on. So instrumentation details should also be mentioned on the field log, and as I mentioned earlier, an incomplete record is really a misleading set of information. Now, soil description, you have to describe the subsurface units that are encountered during the investigation process. Now, soil description should include all those things: density or consistency, structure, field moisture condition, color or odor, particle shape such as angularity, and soil constituent, whether it is composed of sand or whether it is composed of clay or what have you. Now, the first aspect that needs to be included in the description of the subsurface units is density, and density is applicable. This is for coarse grained soils actually. If you recall, coarse grained soils, they derive their material strength basically from interlocking between individual grains. As a result, density becomes a very important parameter affecting the strength of that particular subsurface unit. So here we have got we could have a spectrum of different densities. It could go from very loose to very dense. So very loose is a type of you can infer actually these different densities by conducting very simple tests, such as trying to penetrate the formation by a stick, by a shovel, by the handle of a shovel, or trying to insert a rod into the deposit. For instance, if you have got a very loose deposit, then that particular deposit is easily penetrated with the handle of a typical shovel, whereas if it is loose, then it can be penetrated with a 13 millimeter diameter, approximately 13 millimeter diameter steel rod. Now, if you need to use a 2 kg hammer to drive that 13 millimeter diameter steel rod, then you can say that the deposit is medium dense, and if it is dense, then even after hammering the rod, you would not be able to penetrate a depth of more than say 300 millimeter. If the deposit is very dense, then the penetration is less than about 25 millimeter of the 13 millimeter diameter steel rod. Second thing is consistency. So, consistency actually is applicable for fine grained soils such as cohesive silts or clays. So, these type of soils, they actually derive their strength from intergranular electrical bonds. We will see these aspects later on. They can, the consistency of a fine grained soil can vary from very soft to hard, and here also I mention a series of simple tests that can be performed on a sample extracted while the investigation process is going on, and these tests will tell the inspector whether a soil is approximately very soft or it is hard. Then you have to mention structure, you have to talk about structure of a particular deposit. Now, structure could be massive. Massive structure is relatively homogeneous and featureless, no joints or bedding planes apparent within the unit of soil or rock. It could be homogeneous. Homogeneous is relatively uniform in composition and color. It could be heterogeneous, which means non-uniform in composition and color. It could be layered. There could be parallel layering, or the layers could be pinching or thickening in a particular direction, or there could be laminations. These indicate very closely spaced alternating layers of different soils. Now, if you have got only two different types of soils in terms of grain sizes, then laminated soils are called varved soils. More structural aspects. Structures could be seams. Now, seams are basically layers which are less than 10 millimeter thick, and they extend to great depth, great lateral extents. There could be lenses. Now, lenses are basically similar, but they are of limited lateral extent, similar to seam, but they are of limited lateral extent. Then there could be fissures or cracks or discontinuities within the mass of soil. There could be slicken sides. Slicken sides are essentially joints again, fissures again, but these fissures, the surface of these fissures are very highly polished, they are very slippery. The soil can be cemented, which means there are intergranular cementing agents between individual particles. Then you have to describe moisture, color and odor of a particular soil deposit. Moisture condition could be dry to wet. Dry means there is no visible moisture. Moist means the deposit is moist to touch, but there is no free water, and wet means there is free water, free water film present on the surfaces of the individual particles. Then you have to also describe the color of a particular soil unit, and color have to be described as the sample is dug out of a particular borehole, because color changes with exposure to to exposure to the ambient condition. And color actually include a primary color, or there could be a secondary. You also have to include the description of the secondary coloration, such as patches of a secondary color. This type of patches are often called mottling, and this particular feature is associated with groundwater, with seasonal or with time dependent groundwater fluctuation within layers. So, for example, the layers within which the groundwater level fluctuates, they have often colors which is basically it has got one primary color, say orange, and it has got dark patches, and this particular type of coloration is called mottled orange black. Then there you have to describe the odor, and that is important because, for example, if there is a lot of organic content within a particular soil, then the odor is going to be indicative of such organic content. Then finally, you have to name the soil constituent. Here you have to name the primary constituent of the soil, and this includes say for example sand or clay silt, and you also have to name the secondary or tertiary soil constituent, So here you use qualifiers such as trace, little, some, with, or and the percentage of the secondary or tertiary constituent meant by these qualifiers are indicated over there. For example, if you have got little, if you have got clay silt with sand, that means it is primarily a clay silt soil, but it has got 20 to 30% of sand, and it could also include trace gravel as is given in the example at the bottom of this particular slide. Now we are going to continue with this particular presentation. We are going to continue with the description of rock units when we meet in the next presentation, and we are going to look at the details of how the information gathered during the subsurface investigation, the systematic information gathered during a subsurface investigation, they are recorded, and after that in the next presentation itself we are going to move on to the intrusive testing methods. Okay. With that, actually I am going to wrap this particular presentation here, and we are going to consider the question set of this presentation together with the question that is going to come once we complete the lesson in the following presentation. So until we meet for the next time, bye for now. Thank you very much.